Hey all, so in this video we're going to look at graphs of polynomials. There's a fair bit of stuff to learn before you actually graph them in terms of the behavior, but once you have that down, the graphing actually ends up being fairly easy. Getting good at this section will also help with the section later in the quarter, so it's kind of a two-for-one here. For this first one, we're asked to find the degree, the leading coefficients, and the maximum number of real zeros of the polynomial. And so this is just introducing a little bit of terminology and some definitions. To find degree, leading coefficients, what we want to do is make sure we're looking at the actual leading term. So if I wrote this in descending order, 6x to the 6th should actually be before the minus 3x to the 4th. So we're counting down 7, 6, 4. That said, the term that we're actually interested in is the one with the biggest power, because that's going to be our leading term. So with that, the degree of the polynomial is whatever the highest power is. In this case, it would be degree 7. The leading coefficient is exactly what you would think. It's the number in front of the leading term. So I'll abbreviate it. Leading coefficient would be -2 in this case. And when we get down here to end behavior, we care about both of those things, which is why we're giving them a name up here. And then what was the other one? Maximum number of zeros. So max zeros is going to be the same as the degree of the polynomial, which makes some sense if I have y equals x, a linear function, which is to the first. At most I can have 1, 0. If I have y equals x squared, which is our parabola, at most I can have 2 zeros. For a cubic, it can have 3 zeros, and so forth. So max number of zeros matches the degree. This one's the exact same thing, except they kind of buried the lead over here. That makes it look like it's negative. Do that. They put the leading term on the end, so you do have to make sure that you're looking at it in descending order. So this would be degree 8, leading coefficient of a +2, and max 0 same as the degree, so that would be 8. Why we care about all that is right here, and this is end behavior for power functions. So there are kind of four things that can happen. We could have something like x squared, we can have something like -x squared, we can have something like x cubed, or we can have something like -x cubed. So we can have even powers or odd powers, and we can have positive leading coefficients or negative leading coefficients. So that's kind of the 4 possibilities in terms of the leading term. I'll do a little bit more with what this says down here, but let me stick with this box for a second. So if I have even power and then k greater than 0, so in other words, what I would call positive even, it's going to look like an x squared. Like even if it's x to the 100th, if you zoom back far enough, it's going to end up kind of looking like x squared, in that the parabola is going to, or the function is going to start from the positive, come in, and then leave back out going in the positive y direction. Likewise, if I have something that's a negative with an even power, it's going to eventually, at least in terms of these where it's coming in and where it's leaving out, it's going to look like -x squared. Odd powers look like x cubed. They also look like the line y equals x. That's another odd one that you can think of. But they come in from negative infinity, they leave out positive, and then there's the reflection of an x cubed right there. So what this table does is kind of lets you know for any function what the end behavior is going to be, which way it's going to kind of come in towards the middle of the graph, and which way it's going to leave out. When we're looking at, it depends on the form, and we'll see that down here. If the function is factored, we have to add together the powers to find the leading term. So 5x cubed down here is not the leading term, because if I multiplied that, I would get 5x to the 5th. And then that would be my leading term. So you have to add together the powers of x's, or kind of think about if you multiplied it out, what would that be leading as? If there's no factoring happening, you can just look at the leading term right there in front. So let's take a look at these. This one is going to be, like I said, if I distributed that 5x through, I would have 5x to the 5th, which means it is positive because this 5 is positive, and odd because the power is odd. So positive odd looks like x cubed. So as x goes to negative infinity this way, the y's go to negative infinity. And as x, this arrow means goes to positive infinity out this way, the y values go to positive infinity. For that next one, that would be a negative even, because it starts, the negative 7 has a negative coefficient, so it's going to have a reflection, and the 4th power means it's even, so that means it's going to look like this one right here. So as the x's go to negative infinity, the outputs also go to negative infinity, and as x goes to positive infinity, then the outputs also go to negative infinity still. So scroll that down a little bit more. Let's see, this one, so this is factored out, so we have to kind of count them. So this would be 1, 2, 3, 4 x's. So if I FOILed all that out, I would have x to the 4th, which is positive even, so that's going to look like x squared. So as x goes to negative infinity, this will be positive infinity. Likewise, as x goes to infinity, it would be positive infinity. And the last one we have negative. There's 1x there, there's 2 there, there's 2 there. So if I FOILed, I'd have negative 2x to the 5th. And so for that one, that is negative odd, which would be this one right here. So as x goes to negative infinity, these go to positive, and if x goes to positive infinity, the outputs go to negative infinity. So x-intercepts and multiplicity. To find the x-intercepts, or also called the zeros of a polynomial, you set y to 0 and then factor, or just solve for x if it's already factored. To find y-intercepts, if you need to, you would let the x all equal 0, and then that will give you the y-intercept. And then the multiplicities, another one of our definitions, is the power that the zeros, the x-intercepts, are raised to. The sum of the multiplicities is the degree of the polynomial function. So for example, right here, this has a 0 at negative 3, multiplicity 4, because that 4th power right there. And then it has a 0 at 2, because x minus 2, what would make that 0 is positive 2, and that's multiplicity 5. In terms of the multiplicities, even powers, so even multiplicities are going to come down and bounce, just like x squared does, so they're going to come down and just touch the x-axis. They could also come from the bottom and touch the x-axis that way, but they're not crossing. For odd multiplicities, we'd have something where at those intercepts, it would be going from below the x-axis to above, so it actually crossed through at the intercepts. And again, all of this seems like a bit of information, and then we put it together, and it makes it really easy to graph things in just another second here. So for this couple of examples, we're supposed to give the 0, the multiplicity of each, state the behavior at each 0, which is bounce or cross is what I'm looking for there, and then state the end behavior, which is that last table that we looked at. So let me make a little, so the zeros for this one are going to be 2, negative 3, and negative 4 from each of those factors. The multiplicity of each of those zeros, so just kind of do like this. For 2, the multiplicity would be 3 because it's the 3rd power. For the negative 3, the multiplicity would be 2 because there's 2 factors there of 2 plus 3, and likewise this one would be 2. In terms of the behavior, we're looking for bounce cross there because that will be important when we a graph in just a second. So since this is an odd multiplicity, it doesn't matter the even odd of the zeros. What matters is the even odd of the multiplicities. Odd multiplicities are going to cross, so I'll just call that C for cross. Even multiplicities are going to bounce, so both of these two would bounce. And what was the last thing? Probably the end behavior? Yes, the end behavior. So if we count this up, we'd have 3, 4, 5, 6, 7 with a negative. So if I FOILed all that out, I'd have negative, oops, not x, but t to the 7th. So this would be negative and odd. And with that information, I'll be able to graph these here in a second. I kind of almost want to do one right now, but I won't. I'll wait until we get to the ones that I'm graphing. Same question here, so I'll just kind of do the same order, not rewrite it all. So I would have a 0 at negative 4, I'd have a 0 at 3, and I'd have another 0 at negative 3. And this will be multiplicity. There's nothing there, so that's an invisible 1 for both of those, and this one would be 2. Odd multiplicities cross, so that'd be a cross, and that one's going to be a bounce. And then this is negative 1, 2, 3, 4 x's, because that one's squared. So negative 3x to the 4th means this one is negative even. I think just to show how all that would work together, I'm going to go ahead and graph this one real quick down here, just to kind of preview what's coming up. Why we would care about all this. So let's see, negative 4, negative 3. I'll call that one 3. So that's all the places where I'm going to cross the x-axis for this function. It's negative even, which means it should end up looking something like that. In other words, it's going to come in from negative infinity and leave out negative infinity. At negative 4, I'm going to cross. Change colors here. And at negative 3, I'm going to bounce. So we're going to cross on negative 4, bounce off of negative 3, and then come back and cross on 3. So that's how we're going to tie all that information together. Is if we know which way it's coming in, where it's going to cross or bounce, we can have a graph of the function. This last one, same basic thing here. Change back. We have zeros at 4, negative 4, and 1. And let's see, this is going to be multiplicity 3, 1, and 3. And that's going to, they're all going to cross because they're all odd. And this would be 3n to the 3, 4, 5, 6, 7. And so this one is positive odd. Okay, so then we get into graphing the polynomials proper. Lots of cubics on this one, just as it's sort of what I had to choose from in terms of the problem sets. It is good to be able to graph other ones because, like I said, in later sections this is going to come back. We'll use it for solving inequalities, but these ones will be fairly friendly. So for this one, to graph this, we're going to do kind of all the things we just did and then draw the picture with it. So we would find our x's. They're going to be 3 and 1. And this one's going to bounce because it's multiplicity 2. That one's going to cross because it's multiplicity 1. And I have 1, 2, 3 x's. So this is x cubed in terms of the shape. And so it's going to come in from the bottom and leave out the top. So we got a 0 right there at 1. We have a second 0 right there at 3. If you're graphing these on paper, for me, I'm not real worried about the y-intercepts. There's also the issue of how high. So like for this one, I'm going to come in from the bottom. I'm going to cross on 1. And then come back and I'm going to bounce off a 3 and then kind of continue up from there. Just try to make that look a little smoother. But that's the basic idea. We're not worried about how high these bumps are, which is always something that people ask in class. That actually takes calculus to find that efficiently. So we're not worried about that at this point. What we want is the shape to be right, because that's actually what we're going to end up using these for solving inequalities. And then when you're in calculus, it means you'll be able to look at this and have some information in terms of things you would look for in that class. So general shape is all we're looking for, not super accurate graphs. For this one, we got x equals -1, -3, and -4, and those are all going to cross because they're all to the first power. So -1, -3, -4, 1, 2, 3 x's, so another x cubed. I think these all ended up x cubes just because it was what I had to choose from. So we'd cross on 4, cross on 3, and cross on 1. That was probably the worst looking one of those ever, but let's see, we'll try that one more time. Probably not going to be very well with this. And again, so this is probably not accurate. The y-intercept on this one should actually be way up there at 12. So not worrying about the accuracy in terms of how high and how low the graph is going, but I want the right behaviors, and where it should be above the axis, I want to see that. Where it should be below the axis, I want to see that. So another x cubed. This one's going to be x equals 4 and 2, and this is going to bounce, and this is going to cross. So there's 2, there's 4 cubes, so it's going to come in from the bottom. We're going to bounce off of the 2 and then come back and cross on the 4. For this one, x is 0 and -3 with a bounce at 0 and a cross at -3. So there and there. So crossing on -3 and then bouncing off of 0. These next couple we're given the picture of the polynomial, and then we are asked to solve for the equation that would produce that picture. So kind of like we did with vertex form and parabolas, we're going to use y equals a for that stretch constant that we're going to have to solve for. And then we can look at where we have intercepts on this picture and use that to get our factors. So this first one, we have an intercept at -4 right there. So that means I must have factors of x plus 4 to get -4 to be a 0. And since that is coming down and bouncing, that's going to be a squared. I have an intercept at 1, so that means I had to have had a factor at 1, or -1, excuse me. And an intercept at 2, so I have to have a factor with a -2. And then the last thing we need is one clean point that we can read. So for us, it's often going to be that y-intercept. So when x is 0, y is 2. That gives me a point that satisfies the equation I'm trying to write, and then I can just plug that in for x and y and use that to solve for a. So 2 is going to equal a times, this would be 0, so that becomes 4 squared, times -1 times -2, or 2 equals 16 times 2, that would be 32. I'll just leave it on that side since I have it over there. Divide the 32 over and reduce, and we should have a equals 1/16. So my equation would be y equals 1/16, and then all that stuff right there. Next one's pretty similar. It has a little thing here where the graph goes up off of the graph. That is okay. The part that we care about is right here at these intercepts. So we just have to be careful to catch all of those. Again, we'll set it up y equals with an a, so we can figure out what that constant would be, and we'll just go right in order. So that's crossing, so the next one is bouncing after that. So we have x plus 2, x plus 1 for the -2, -1, and that 1 we'd have an x minus 1 would be the factor, and that one has to be squared because we're bouncing there, and then careful not to miss this one over here, and that is x minus 4. And looks like from our intercept again is 0, 2, right there for our y-intercepts. We'll plug that in for x and y. So 2 equals a 2 times 1 -1 squared times -4. So that would be 2 and then a. -1 squared would make +1, so this is 2 times 1 times 1 is still just 2 times -4. So I think that's a -8 over there, and divide that over and we get a equals -1/4. And so the answer should be all of this, but with that -1/4 right there, and I'll just pass on writing all that out again. And the last one is basically the same thing, except now we have a verbal description instead of a picture. So polynomial of degree 3 has a root multiplicity of 2 at x equals 4. So let's go ahead and start getting that set up. So if equals 4 is a solution, bring that over, and x minus 4 is the factor, and that's multiplicity 2. And a root multiplicity of 1 at x minus 5, so when I bring that 5 over, it's x plus 5, and that would be to the first. The y-intercept is -40, so that means when x is 0, y is -40, find the formula. And then it's the exact same thing as what we just did. We'll throw our -40 on that side, and our zeros in here, so we'd have a, that'd be -4 squared times 5. And let's see, so -40 equals a times, this would be 16 times 5 is 80. And then dividing the 80 over, that should reduce to -1/2 for a. So final would be y equals -1/2 x minus 4 squared,